So let us start with another problem so as to get a clear view of the analysis of rectangular section. Let us try to understand the moment of resistance and something more than what we have done in the previous problem. Now over here we have been given a RCC beam 250 mm wide. The width has been given as 250 mm by 450 mm effective depth. Over here the term effective depth has been clearly mentioned as 450 mm. So we know that effective depth is the distance from the compression fiber, the topmost or extrememost compression fiber, to the center of the reinforcement. The vertical distance that is given to be 450 mm. This beam is reinforced with 3 bars of 20 mm diameter. So as we see over here on the right hand side in the picture, there are 3 bars of 20 mm diameter placed symmetrically. Now if M25 grade of concrete and Fe415 steel has been used, find the moment of resistance of the beam and the UDL, the uniformly distributed load it can carry over entire its span if the effective length of the beam is 4 meters and the beam is simply supported over its supports. So now this problem expects us to do something more than just the previous problem. In the previous problem we had to just find the capacity of the beam, we had to find only the moment of resistance, but now we have been given a realistic problem. The beam is there, a beam is existing, it is having 250 mm as the width, 450 mm as the effective depth, it is reinforced with 3 bars of 20, and we have been told that this is a simply supported beam. It has an effective length of 4 meters, and now we are supposed to find out what is the UDL it can take. What UDL can be permitted on this beam? What is the maximum UDL which it can take? So now let us start with the solution exactly in the same fashion as we had solved the previous one. Now the data given over here is B is 250 mm, the small d is 450 mm, small d is the effective depth, AST indirectly has been given to us as 3 bars of 20 mm dia. Please note, mostly everyone will be mentioning the AST only this way. The number of bars will be given and the diameter will be given. Now when the number of bars and the diameter is given, it can be a same bar with number of bars, same bar with numbers whatever, or it can be a combination of different diameter. So it can be either the same diameter with different numbers, it can be 2 bars, 3 bars, whatever, or it can be a combination of 2 different or 3 different diameters and the number. Now in this case also we have been told that it is area of steel as 3 bars of one single diameter, that is 20 mm itself. We have been told that there is M25 concrete and Fe415 steel. The effective span small l is 4 meters and it's a simply supported beam. Now what are we asked to find out? We have been asked to find out moment of resistance of the beam and the UDL which can be permitted on its span if it is a simply supported beam. Now in the calculations, as in the previous one, our step 1, calculate the value of XU by D from IS clause G1.1a page 96, that is IS 456 2000. So that's the one which has been given over here, XU by D. Please remember, as I have mentioned earlier, this XU is the depth of the actual neutral axis, the existing neutral axis. So XU by D is equal to 0.87 Fy AST divided by 0.36 FCK B into D. So determine the depth of the neutral axis from this particular equation. Now XU by D is equal to 0.87 is just a number. Fe415 steel has been given, so Fy becomes the yield stress of the steel is 415. AST we have been given indirectly, so we will be doing the calculations. The area of steel is 3 bars circular area, 3 bars of circular area, so pi d square upon 4, where d is 20 mm. So 3 multiplied by pi by 4 into 20 square. So this becomes A is equal to 3 into This area comes to 314. So area comes 3 into 314 as 942 mm square. So we have the area of steel as 942 mm square. Now this value of 942 is substituted over here for AST. So AST is written as 942. Coming down, 0.36 comes down as it is. Now FCK has been given to us, grade of concrete has been given to us is 25. So FCK is written as 25. Width of the beam in this case is 250 mm and the effective depth is 450 mm. So having got all these values, the value of XU by D is calculated. The value of XU by D comes equal to 0.34. With this calculation, that is 0.87 into 0.87 into 415 into 942 divided by 0.36, 25, 250, 450, which are all in the denominator, we get XU by D, the left hand side, equal to 0.34. Now we go to the step number 2. In step number 2, check the value of XU maximum by D, the ratio of limiting neutral axis, the maximum value of neutral axis which is possible based on IS 456 clause 38.1. It is given in the note page number 70. So now over here the limiting values of depth of neutral axis for different grades of steel. Please remember, as I have mentioned earlier, these values XU max by D are dependent only on the type of steel. They are independent of the type of concrete. So based on the type of steel we get the value. So over here, since it is Fe415, for Fe415 where the yield stress is 415, the value of XU max by D is 0.48. So therefore for Fe415 XU max by D is 0.48. Now please note, XU by D is 0.34, XU max by D, the maximum one which is possible, is 0.48. The actual one is 0.34, the maximum one is 0.48. Now going further to step number 3, compare the values of actual neutral axis to effective depth, that ratio, and the maximum depth of neutral axis to effective depth, the ratio. So actual neutral axis to the effective depth, the value is 0.34. We find that it is less than maximum value of neutral axis to the effective depth, which is 0.48. So 0.34 is less than 0.48. Now what do we infer from here? Step number 4. When XU by D is less than XU max by D, the beam is a under reinforced beam. We find that the beam is under reinforced beam. So that's our inference, very important inference which we have got. Now based on this, if it is under reinforced, how do we calculate the value of moment of resistance? In IS 456 clause G1.1b, page 96, we get the value of mu as if the value of XU by D is less than the limiting value, calculate the moment of resistance by the following formula. So that's the formula given. Mu equal to 0.87 Fy AST into D into bracket 1 minus AST into Fy upon B D FCK. So mu is equal to 0.87. 0.87 value comes down over here as it is. Fy, the type of steel, the grade of steel which we are using, the yield stress of that is 415. AST, which has been already calculated, is 942. The effective depth is 450 into bracket 1 minus AST is 942, which has been calculated. Fy we already know is 415. B, the value of B is the width of the beam, that is 250 mm. The effective depth of this particular beam, effective depth is given to be 450 mm. The characteristic strength of concrete, the grade of concrete, is 20. So finally that 20 comes over there. This 20, all the values are known. We can easily calculate this. When we calculate this, we get the value of mu. the ultimate moment which it can resist is 126.46 into 10 raised to 6 Newton mm. So the ultimate moment, this beam with this reinforcement, this cross section, this grade of concrete and steel can resist, the ultimate moment is 126.46 into 10 raised to 6 Newton mm. Now moment of resistance, now that was the ultimate moment it can resist. Moment of resistance is obtained by dividing 1.5, that 1.5 is the load factor to get the actual moment of resistance. So moment of resistance is the ultimate moment which it can resist divided by 1.5. So 126.46 into 10 raised to 6 divided by 1.5 gives me the moment of resistance of the beam as 84.30 into 10 raised to 6 Newton mm. So the moment of resistance of this beam is 84.30 into 10 raised to 6 Newton mm. I would like to convert this Newton mm to kilonewton meter. Newton mm to kilonewton meter. 84.36 into 10 raised to 6 Newton mm is equal to 84.3 multiplied by 10 raised to 6. Please note, from Newton to kilonewton, Newton is small, kilonewton is larger, so we divide by 1000. Similarly, from millimeters to meters, millimeters is small, meters is larger, 1000 millimeters is equal to 1 meter, so 1000 is down. So when we solve this, we get 84.30 into 10 raised to 6 Newton mm will be equal to 84.30 kilonewton meter. So we get the moment of resistance of this beam as 84.30 kilonewton meter. Now we have been asked in this problem to find the moment of resistance of the beam, and apart from that they have also asked us to find out how much UDL can be permitted on this beam. So we have got the actual moment of resistance of the beam. Now moment of resistance when a beam is simply supported with UDL, we have the maximum bending moment which can come on the beam is WL squared by 8. Maximum bending moment which can come on a simply supported beam with UDL is WL squared by 8. In the worst condition, the moment of resistance is the moment of the internal forces should be equal to the external acting bending moment, that is WL squared by 8. The maximum bending moment which is acting on the section is WL squared by 8 for a simply supported beam fully carrying UDL. WL squared by 8, that is the external bending moment. The internal bending moment created by its own forces, that is the forces in compression and those in tension, that is the moment of resistance. So in the worst condition we have, or in the equilibrium condition, the equilibrium of forces, we have the moment of resistance becoming equal to the maximum bending moment. So over here we have moment of resistance equal to WL squared by 8. So given this equation 84.30 kilonewton meter, please note over here when we are using the moment of resistance, the units of this are kilonewton meter. So that's why W over here will be kilonewton per meter and L over here will be in meters. So W over here is kilonewton per meter, L over here is in meters because this is in kilonewton meter. Having got that, W into the effective span is given to be 4. So 4 square by 8. So 84.30 is equal to W into this value comes down to 16. 8 comes down as it is. And when we solve this, we get W is equal to 42.15 kilonewton per meter. The UDL which can be permitted on this beam is 42.15 kilonewton meter. Maximum UDL which can be permitted on this beam is 42.15 kilonewton meter. So the answer is the moment of resistance of the beam is 84.30 kilonewton meter, and the UDL it can carry, the uniformly distributed load it can carry over entire its span is 42.15 kilonewton meter. The UDL it can carry is 42.15 kilonewton meter. Now the question is, the UDL it can carry over entire its span is 42.15. If I want to round it off, can I round it off on the higher side or should I round it off on the lower side? Please note, be careful over here. Always we need to be extremely careful when we are rounding off. If we are leaving the value as it is, there is absolutely no problem. But when we are rounding off, suppose this 42.15 we round off and say that the UDL it can carry over entire its span, we permit anything more than this, say 42.15, I say 42.2 or say 42.5 or say 43 kilonewton meter. The result of that will be, if the value is more than this, if the value of the UDL is more than this, please note this W will increase. As this W increase, the right hand side value will be more than this value. When the W value increases more than 42.15, the right hand side value will be more than the left hand side value. So moment of resistance will remain 84.30, but external acting bending moment will be more than 84.30. The beam could fail. So if at all we have to round it off to permit how much UDL it can take over the entire its span, we can round it off on the lower side and say we can permit 42 kilonewton per meter. There is absolutely nothing wrong, because if I take 42 kilonewton meter, this value becomes 42. 42 into 4 square by 8. Certainly the answer on the right hand side will be lesser than this. Moment of resistance, its internal capability, its internal capacity is more than the external acting bending moment. The beam will be safe. If we round this off on the higher side, your problem, your answer will be termed upon as wrong, because your basics themselves have gone wrong. You have not understood the concept of external bending moment and the internal resisting moment, that is moment of resistance, internal resisting moment. So when the external acting bending moment becomes more, the beam could collapse, the beam could fail. So we need to round it off on the lower side. Best option, if we are not sure, leave the value as it is. So the UDL which can be allowed over entire the span of this particular beam is 42.15 kilonewton meter. Sorry, kilonewton per meter.